Hope all of us are doing great. I'm Ernest, and this is Ernest Sciences and the Mathematics TV channel. Before we proceed, I'd like to appreciate our incoming members and also request us to continue subscribing to our channel and also engage us in the comment section. And check our description boxes for various videos. There's a link I normally put there for similar discussions. So in this specific discussion, we're going to look at the concept of a particle in a box. And of course, basically, we are going to look at the concept of allowed energies. Now, in our last discussion, I had given an example of a description of a particle in a one-dimension box. And of course, I had given it in terms of this specific illustration on our right side of the board. So in this case, this is going to be an increase in the energies and an increase in the value of this particular quantum number for n, which of course is indicating the energy levels given in that specific order. So in this case, I've given a general function for description of the eigenvalues, which basically are going to represent the energy values of these specific levels for n1 continuously as we ascend in that specific order. So we add this specific general description, whereby we said L is going to represent this range or the boundaries between the x0 and xl given as such. And of course, m is going to represent the mass of this specific particle under consideration, and h is Planck's constant given as such. So as we send the values of n, we are going to obtain different permitted or allowed energies. And the energy of electron, of course, as we said, is going to be quantized, which means it's going to appear in discrete units, of course, which are going to be in terms of these numbers of n, as we're going to give it as such. So for our one-dimension box that is shown on the right side of the board, the value of the quantum numbers are going to be inversely proportional to the square, or inversely proportional to the mass and the square of the distance or the width of this specific wall. And the permitted energies of this specific case, of course, are going to be achieved by having these values of n, as I've said. So we can represent the general case for this, as we said, by having a substitution of this specific value for n. And this case, I said that this basically can be simplified using the various range of constants we had given for the Planck's constant, which we can do a substitution for that. And then we're going to have 8 times mass of an electron is also a constant value. And then we're going to have it -31 times this specific. So this is going to be L. So suppose L is given in terms of angstroms. So suppose this is 1 angstrom, which is equivalent to 10 meters. We can consider a case of this specific, of course, a box, and do a substitution for this. So therefore, the square of 10 raised to -10 is equivalent to 10 -20 given as such, and that is going to be in terms of meters. So we have converted this specific length of 1 angstrom in terms of meters, which is 10 to raise to -10 given as such. So this basically gives us a value for the eigen value for this equivalent to that 8n squared v given as such. And of course, we're going to see that this is going to be in terms of electron volts. We can do a substitution for this specific particle for the charge of an electron, but in a simplified version, we're going to have the first energy for the value of n equivalent to 1, therefore substituted for E1 equivalent to 38 electron volts. So this first E1 is equivalent to 38 electron volts. If we consider this width of this particular box equivalent to 1 angstrom. So this is going to ascend in that specific order. We had said that for the second energy for the value of, and let's consider the case of, perhaps we can just do away with this. If we consider the value of a case of the value of n equivalent to 2, we're going to have this energy substituted for 4E1 as we had said. So this is going to be given in terms of 4. So the value for E1 is 38. So this is 38 electron volts, and having a multiple of this, of course, 38 by 4, this is 152. So we're going to have E2 given in terms of 152 electron volts. And in that case, if we do a respective substitution for that one, E3 is going to be equivalent to E times 9, and that is equivalent to, of course, 342 electron volts. So if you consider the range between E1, 38, 152, and the 342, this appears to be ascending in a very wide difference, of course, but as we're going to see that if we consider this one to be a, microscopic, at microscopic level, the dimension is going to be very small, and of course these particular energies are going to be appearing as close as contrary to how we can be able to look at these specific magnitudes in terms of E1, E2, and E3 respective for these specific values. So basically the values for E1, E2, E3, E4, E5 are going to constitute what we refer to as allowed energies. And as I've said, these are going to appear in terms of discrete values which we have mentioned basically going to be quantized energy levels. So in this case, I hope that this particular explanation has given us a general way in which we can be able, or we can calculate the allowed energies given this one dimension, of course, a box that we have given on the board as our example. So catch us in our other videos, and kindly check our description boxes for various links of other videos which are similar, and they're going to assist us, of course, have an overall overview of these symbol systems in quantum mechanics. So that is it for now, guys. Bye, God bless you. Catch us in our next video.